This is kind of a fun section. It's on complex numbers. So more than likely this is probably new to all of you. But the fun part with this is right away you're just like, why do we do this? And by the end of it you go, oh, I see where we could use this at. Well, a complex number is written in the form a plus bi, where a and b are real numbers, they're actual numbers. And I, this is one of the important things, is going to stand for the square root of -1. Well, if we remember back when we first introduced square roots, can you take the square root of a negative? Let's just try it out here quick. Square root of -1. No, it doesn't work. Okay, so that's why we want to write I for the square root of -1, because we want something to represent roots of negative numbers. Okay, and since it's not real, we call it imaginary. So we use the letter I to represent the square root of -1. So the most important thing with that is that you know that I represents the square root of -1, and that if I would square I, what would I get? And if I were to square I, that means I could square the square root of -1, which cancels the square, so that leaves me with negative. So this is important as well, that you know that I squared is actually -1. Okay, that's going to be nice and useful for us. All right, if we break it up, so a complex number is made up of the imaginary part, the part that contains the I, and the real part, so just like any constant that goes with it. So we call this the a plus bi form, so like a number plus the imaginary number that has a coefficient. Let's think about all of our numbers that we've worked with so far. Real numbers, that's like every single number besides our imaginary ones. Okay, so that's like everything besides the imaginary. So that includes all this stuff. It includes irrational, fractions, rationals, integers, everything. And think about irrational numbers. Which ones are what separates rational from irrational? Well, irrational have never-ending decimals. So like pi, the square root of 7, things like that. So rational numbers are decimals that repeat or end, and any other number. So like 4, -7.2, 1/3, things like that. Fractions, well, any type of fraction. Most of those are rational numbers as well. All of them are rational numbers, actually, as you can see here. And then we have integers. Remember, integers are things that don't have decimals, are fractions. So like -4, 7, 28, all those kinds of things. 0 is also an integer, and 0 is kind of its own separate number. And then we have negative whole numbers and counting numbers. Counting numbers are like our whole numbers, like 1, 2, 3, 4, so on and so forth. Negative whole numbers would be just all my negative counting numbers. And so, real numbers are made up of all these things. Rational numbers are made up of all of these things. Okay, so on and so forth. You can kind of see how that works. And then when I add my complex numbers, remember, everything is a complex number. Everything is. But if there's an imaginary with it, that's kind of its own separate case. Imaginary numbers are totally different than everything else, but complex contains everything. So if I just had the number 4, it would technically be complex, but it also would be a counting number, it'd be an integer, it'd be a rational number, it'd be a real number, but it wouldn't be fractions or irrational or things like that. And on a number or on a coordinate plane, what it looks like is our x-axis now is what we call the real axis. And our y-axis is going to be our imaginary axis. So this is going to contain our I. So if we look at some of these coordinates here, so it's not like an ordered pair. It's going to be something written in that a plus bi form. That's how we graph it. Well, to do the a, that's just going for our x-axis. So for example, we look at this green guy. It went over 4, and then up 2 units in the imaginary direction. And that's where we came up with that 4 plus 2i. We look at this blue one. It went left 3, 1, 2, 3, and it went up 4 units in the imaginary direction, right? So left 3 and up 4. And the red one, it went -5 and down 1, right, in the imaginary direction. So the imaginary axis is the y-axis. That's the important part. And we'll come back to that in just a little while here. So arithmetic with complex numbers is not complex, right? You just treat it as a variable. So 2i plus 5i is 7i. 2i times 5i is 10i squared, but be careful, we always want to simplify things. Well, what is I squared? Remember, I squared is -1, right? Because I is the square root of -1, and if I would square it, they cancel. So that's where I can rewrite this as -1, so 10 times -1 is -10. So this simplifies to negative 10. So that's where our imaginary numbers, we want to write it all the way simplified. So let's try a few more of these guys. Plus sign means I can just drop my parentheses, don't have to worry about those. So I'd have a 2i and a 7i for 9i, and then 5 and a negative 3 for a 2. And I like to write it with the constant first before the imaginary, right? Because you get in that a plus bi form. Nothing I can simplify there, so I'm done. How about here? Yep, run through our FOIL. So we got 5 times 3. We got 5 times negative 4i. We got 2i times 3. And then we got 2i times negative 4i, which is negative 8i squared. Let's simplify things. So we got these two combined to give me a negative 14i. And remember, I squared is really negative 1. So negative 8 times negative 1 is positive 8. And then I can combine my 15 and my 8 to give me 23 plus, minus 14i. 23 minus 14i. Always write it in that form, a plus bi. So put the constant first and then the imaginary number. Okay, I think we're kind of getting the gist. We don't need to go through the rest of these. I want to look at this guy, though, this last one right here. If you notice, these is like the factored form of our difference of squares. So if our terms match and we have a plus and a minus, let's watch what happens. I get 6 times 6, which is 36. And if we remember, our middle terms should cancel, right? Because I'd have a negative 6i and a positive 6i. So they end up canceling each other. And then lastly, we have I times negative I, which is negative I squared. So what do we really get here? We get 36 and minus I squared. Well, what is I squared? That's a negative 1, so it's really minus negative 1, which is really plus 1. So we would get 37. Ooh, that's kind of fancy, right? So we have a term for this when we multiply by its like opposite sign. We call these guys complex conjugates. Okay, and the product of the complex conjugates always gives you a real number. It always does. And take a look why. Because our middle terms cancel, and we always end up with an I squared in the end. It doesn't matter what number's in front of it. We get an I squared, which we know is negative 1. So that's important because we want to use that in situations like this. We don't want an imaginary number in the denominator. Same thing like we don't want a radical in the denominator. So what do I multiply by? How do I get rid of it? Well, I don't want to multiply by itself. I want to multiply by its conjugate, its complex conjugate. So I want to multiply by 4 minus I. So then I know I guarantee my I will be gone in that denominator. Well, I have to do the same thing to the top then. And if you remember kind of the quick trick that happened, what really happened? It was, you got to really think of your difference of squares. So remember, a difference of squares means you got a square root, or a square and a square, and that factors into a plus b and a minus b into the conjugates. So you really have the square of the first one minus the square of the second one, right? So in this case, I'd have 4 squared minus I squared. And it's always a minus sign, right? Because it's a difference of squares. That's the quick way to do it. Otherwise, you have to go through your FOIL. 4 times 4, which is 16. And then you'd have a negative 4i and a positive 4i, which cancel. And then I times negative I, which is negative I squared. So just remember that rule, and you don't have to go through all that work. And then up top, I got to go through my distributing. So 2 times 4 is 8, and 2 times negative I is negative 2i. And I'll simplify down here. So this is 16. This is really negative 1. So 16 minus negative 1 is really plus 1, so 17. So I'd have 8 minus 2i over 17. And we always want to write it in the a plus bi form. So go ahead and divide each of these by 17. And I get some nasty decimals, but I'm just going to round to the nearest hundredth for now. So I'm going to say 0.47 minus 0.12i. So that would be that guy reduced down. Let's do another one of these. All right, don't want it in the denominator, so what do you think I should multiply by? Well, it doesn't have a conjugate, so couldn't I just multiply by I, as long as I do it to the top? So what would I get? I'd get 6i up top, and I times I is I squared. And I squared is really negative 1, and 5 times negative 1 is negative 5. And if we divide those, we'd get negative 1.2i. And let's do another one with a conjugate. So remember, we multiply by the opposite sign. So 1 minus 2i, which means I got to do it up top, minus 2i. So on the bottom, remember, we really get 1 squared minus this squared, 2i squared. That's a quick way to remember how to do it. So up top, they're not conjugates, so I got to go through the whole FOIL. So 2 times 1 is 2. 2 times negative 2i is minus 4i. Negative 3 times 1 is negative 3i. And negative 3i times negative 2i is positive 6i squared. So sometimes you can skip those steps because you should know that I squareds are really negative 1. Right? I squareds are really negative 1. So up top we have, this is a negative 6 now. And 2 minus 6 is negative 4. And negative 4i minus 3i is negative 7i. And on the bottom we have 1 minus, well, this is really 4i squared. And I squared is negative 1. So that would be negative 4, right? 4 times negative 1. And we have to add those two now because minus a negative, so that's 5. And then we'll simplify, right? Divide both these guys. So I got negative 0.8 minus 1.4i, just like that. All right, I always write in that form a plus bi. Okay, well, where these come into play are our quadratics when there are no solutions. So if I think about this, if I look at the graph of this, x squared plus 4x plus 5, guess what? It does not cross the x-axis, so there's no roots. So usually we have no solution for this one when it's equal to 0, right? But when I bring imaginary numbers into play, I'll get a solution. And we'll show you why using the quadratic formula. So remember, we got what, a is 1 here, b is 4, c is 5, and we'll use our x equals negative b plus or minus radical b squared minus 4ac all over 2a. So let's plug in our information. So we got negative 4 plus or minus radical b squared, so 4 squared, which is 16, minus 4 times a, which is 1, times c, which is 5, all over 2 times 1, which is 2. And that simplifies some stuff here. So negative 4 plus or minus, well, this is really 20. And 16 minus 20 is negative 4. Okay, so here's where it comes into play. Usually we have no solution. But let's think about what we can do here. What I want to do is I want to break this up and almost like take a negative 1 out of it somehow. Right? Because I know the square root of negative 1 is I, and that's important. So I'm going to rewrite this. So I'm going to write this as x equals negative 4 plus or minus. Instead of writing the square root of negative 4, I'm going to write it as the square root of negative 1 times 4. And why would I do that? Because that's really the square root of negative 1, times the square root of 4. And what is the square root of 4? 2. What's the square root of negative 1? I. So I can really write this as 2i. See how convenient that was? Okay, so really we just broke negative 4 into negative 1 times 4. And the square root of 4 was 2. And the square root of negative 1 was I. Okay, and that's still all over 2. And so let's just write my two solutions out so we can take a look. So I'd have x equals negative 4 plus 2i over 2. And I'd have negative 4 minus 2i over 2. And let's simplify those. So divide each by 2 here. So I got negative 2 plus I. And then I have negative 2 minus I for my solutions. And if you notice, our roots are complex conjugates in this case. Okay, pretty convenient. All right, and the same thing would work with this, so we won't go through the process of it. Hopefully you got the idea of how those imaginary numbers come into play.